So they began to start to look at what could be done with low-cost technologies to be able to deliver fiber to the home class services without the fiber. And the model became use commodity technology that's already being manufactured in the millions, and so we basically fixed on using Wi-Fi access points and then dramatically improve the antenna technology that's connected to those cheap radios so that we could manufacture a very low-cost product. What we have wound up with, this is a cardboard mock-up that we started with. Now Arizona State University has actually turned this into a real physical device that we're in the process now of testing and measuring the results. They did extensive computer modeling on it and actually did the physical design of the antenna. And what this antenna can do is that it can switch nearly instantaneously between 5 different faces, and each face, when it's live, or lit up as we call it, connects to the Wi-Fi radio that's built into the bottom of this little box. And so we can listen or send in a particular direction, and then a few microseconds later listen or send in a different direction. Literally between packets we can change the direction of the beam. Because we now have the 5 faces, it creates a very narrow focused beam. And then using MIMO technology that's part of Wi-Fi radios, we can then further steer the beam within the window of each, or the directions that each face is pointing. By increasing this, by turning the beams into these very narrowly focused, instantly aimable beams that can be aimed in any direction, instead of getting 300 or 500 feet between one node and another node in a network, we now can get 2 miles to 5 miles between nodes at the full throughput that the radio can support, which is around 200 megabits per second. So what that means is we can put a network of 500 of these nodes in a residential neighborhood, each node attached to the rain gutter of someone's house, and we can now using the steering capability of the beams and traffic modeling, we can deliver between 50 and 100 megabits of symmetrical service to every subscriber. So we're in the process of moving now from kind of a research and experimental basis to beginning to search for the funding and so on, the seed funding, to be able to commercialize enough of these nodes that we can demonstrate a live community working. Once one community works, this is a cookie cutterable, and we can literally go neighborhood by neighborhood over the entire planet deploying this. What's different about this technology than things like LTE or WiMAX is those technologies which use tall towers are best used for mobile applications where you need to try to reach a fairly wide radius to reach the subscribers that are going to talk to the device, and you tend to wind up supporting a lot of subscribers. So the bandwidth is shared among many subscribers, therefore the amount that each subscriber gets is reduced to a relatively low level on the order of, right today, 4 to 6 or 7 or 8 or 10 megabits per second, which is still pretty good for a mobile application. But we intend this technology to compete directly in the delivery of internet television to people's homes, where 4 high-definition television screens are all being fed different streams with perfect broadcast clarity over those IP streams. And we intend to, at every neighborhood hub for 500 subscribers, we're going to be installing disk farms, capturing all broadcast content as it's initially broadcast and making it entirely available on a random access basis. No box required in the home. Pick up your remote control, look at the index of what's been recorded, and it starts streaming to you immediately from the cache in the neighborhood. So we think that there's a fairly revolutionary television delivery model, and of course it still does super good internet as well.